Welcome to Summarize Science. Today, we're diving into a weather report from our nearest interstellar neighbors, a pair of failed stars just 6.5 light-years away. This new report comes from the incredible James Webb Space Telescope, which is giving us a revolutionary look at the atmospheres of these objects. The celestial bodies in question are brown dwarfs, which are more massive than planets, but not quite massive enough to ignite into stars like our Sun. The pair, known as WISE 1049a and b, are the closest brown dwarfs to Earth, making them perfect targets for study. For years, astronomers have known their brightness flickers, suggesting they have some kind of weather, but the exact cause has been a mystery. To figure it out, researchers used JWST to stare at the system for 8 hours, capturing how their infrared light changed over time. This created light curves, like the ones you see here, which show the rise and fall of brightness for different molecules in their atmospheres. By looking at the light from water, methane, and carbon monoxide, they could effectively probe the weather at different altitudes or depths. For the brown dwarf named 1049b, the story seems relatively straightforward. Its variability is highest deep in the atmosphere and decreases smoothly as you go higher up. This strongly suggests that the primary driver of its weather is patchy silicate clouds, essentially clouds of tiny rock particles, rotating in and out of view. But its sibling, 1049a, is a completely different story. While it also has deep clouds, the variability high up in its atmosphere is surprisingly strong. This pattern doesn't fit with just clouds, because those deep clouds shouldn't have such a big effect on the upper layers. This suggests an additional, more exotic process is at work: thermochemical instability. Think of it not just as physical weather, but as chemical weather. In certain layers of the atmosphere, temperature fluctuations may be causing rapid chemical reactions, changing carbon monoxide into methane and back again. These patches of different chemistry create bright and dark spots that contribute to the flickering light we observe. Based on these findings, the team created these incredible artistic representations of what the atmospheric layers might look like. For 1049a, the atmosphere is depicted with large, planet-circling bands, consistent with the smoother, wave-like variations it shows. For 1049b, however, the picture is much more complex. On top of its planetary bands, the data suggests the presence of smaller-scale spots or vortices, which could be massive storms churning in its atmosphere. So, let's recap the most important takeaways from this groundbreaking study. The James Webb Space Telescope has provided an unprecedentedly detailed look at brown dwarf weather. We've learned that while patchy, rocky clouds are a major factor, they aren't the only one. For the first time, we have strong evidence that chemical weather, active, unstable chemistry in the atmosphere, can be a primary driver of variability. This discovery fundamentally changes our understanding of these mysterious worlds that exist between planets and stars. It suggests that the atmospheres of distant giant exoplanets could be far more dynamic and chemically active than we ever imagined.